Let's get into limits. Chances are we've already seen limits a number of times very superficially throughout our pre-calculus studies, but now we're going to get into them more deeply. And this is kind of an exciting time, I believe, in one's math education because this is where many would say that we are exiting the realm of pre-calculus and we are really starting to get into some official calculus studies. So I'd like to start with why? Why limits? What are they going to allow us to do? And the truth is that there are a number of ways in which limits help us accomplish certain objectives in calculus, and it takes some time to really appreciate all of them, but I'd like to at least start by giving you a taste. A good deal of time is spent in a calculus class trying to find the slopes of curves, or technically the slope of a line tangent to a curve. And again, I'll leave it to a full calculus class to get into why we would want to do that on a deeper level, but I think we can understand pretty quickly with this example. Let's say you're plotting the position of an object as a function of time. So for example, let's say you're recording the position, the mile markers on the highway as you're passing along as time goes by, and you're recording time in hours. And let's say your position versus time curve looks like this. Well, when you consider what the tangent line looks like to this curve at some particular point, so this one for example, let the units give you a clue as to what you're accomplishing when you decide you're going to take the slope of that tangent line. The rise of that tangent line would be measured in miles, and the run of the tangent line would be measured in hours. So when you take the slope of a tangent line on a position versus time curve, what you're getting is velocity in miles per hour. Consider other options. Maybe you're recording expenses for your business and you're measuring time in years. Then the slope of the tangent line would give you dollars per year, how fast those expenses are changing in dollars per year. Or perhaps the volume of water rushing into some container per week. The slope of the tangent line would give you gallons per week as a rate of change of the water in that container. So again, generally the slope of a tangent line gives you the rate of change of some function. And quite often you're dealing with time on the independent axis. So let me give you a preview as to how we're going to find the slope of a tangent line in a calculus context. Here's a function f of x, and first of all let's observe that the slope of the tangent line changes depending on the point of tangency that we're interested in. So that tangent line is changing and the slope of the tangent line, the rate of change is certainly changing. But let's go back to where I started at the point 2, 4. If I want to find the slope of that tangent line, I've got a bit of a problem. I don't know anything about that tangent line except that it goes through that single point 2, 4. I don't know the coordinates of any other points on that tangent line. And I need at least 2 points to determine the slope of a line, but I only have that 1 point, 2, 4. So here's the very clever trick we'll play in calculus to find the tangent line and specifically the slope of the tangent line. Let's instead consider a secant line, a line that passes through 2 points on this curve. There, so in blue I have the tangent line, and in red I have the secant line going through points A and B on the curve. And of course, those are two different lines. The slope of that red secant line is different, is steeper, is higher than the slope of that blue tangent line. But watch what happens when I start bringing point B closer to point A. As I bring those 2 points closer and closer together, specifically as I take B and slide it along the curve and bring it closer and closer to point A, notice what's happening to that secant line. It is getting closer and closer to the tangent line. It's looking more and more like the tangent line until at some point the points are so close it's hard to even distinguish the secant line and the tangent line. And notice that because I have 2 points of the secant line, I can find the slope as well as other properties of that red secant line. I've got the coordinates of both points A and B. So let's now think specifically about what's going on with the slope. Right now with point B relatively far away from point A, I see that the slope of the secant line is 5.78. The rise over the run is 5.78. And keep an eye on that number as, once again, I start bringing point B closer to point A. First of all, notice that both the delta y and the delta x values are both shrinking, but the ratio is gradually lessening. As you see visually, the red line, the red secant line, is becoming slightly less steep. You notice in the calculation there that the slope of that line right now is 4.8. As I keep bringing the points closer and closer together, it's continuing to decrease. And now the red line is starting to look more and more like the blue line. It's getting pretty close, and we think, wow, that tangent slope must be somewhere in the neighborhood of about 4, a little bit less than 4.17, 4.14, 4.1. And let me even zoom in a little bit here. Even as I zoom in, it's kind of hard to tell those two lines apart. If I continue to decrease that distance, we really start to become convinced that it looks like that slope of the red line and therefore the blue line is approaching 4, right? We become quite convinced that it looks like it's going to reach 4, but then we're denied this pleasure of seeing 4 actually appear on the screen, because once A and B have the same location, once B lands right on top of A, I've got a slope of 0 over 0. And that is something that we'll speak more on later, but that's officially called indeterminate form in calculus. That means that we don't have an answer. There is a slope of that blue line, to be sure, but 0 over 0 isn't giving me that slope. So I never got to see the number 4 appear on the screen, but I became quite convinced, and hopefully you are too, that it sure looks like that slope is approaching 4. And that is the vocabulary, the language we'll use too, is approaching. The slope is approaching 4. So our job in calculus is then to try to convince ourselves that not only is the slope of the secant line approaching 4, but we want to convince ourselves that the slope of that blue line, that blue tangent line, is exactly 4. So for a student new to this, here's what I would propose you should write down in your notes here. The slope of the secant line is just the same old rise over run that you've known about for years, delta y over delta x. I would advise you to draw this picture and make sure you're comfortable with that concept, that slope of secant line is delta y over delta x, change in y over change in x. But the slope of the tangent line, which we have likely already talked about in class, we will call that the derivative of f of x. It gives us the slope of the tangent line, and we'll use this notation, f with a little apostrophe. We say that out loud as f prime of x. The slope of the tangent line is essentially what you get when you take the slope of that secant line, when you take that same delta y over delta x. And remember, we can't let delta x or delta y actually equal 0. So what we'll do instead is we'll essentially ask the question, what happens as delta x approaches 0? What happens is I take that delta x value, as I take the run in my rise over run, and drive it closer and closer to 0, make it a smaller and smaller number. We can't let it equal 0, but we'll say the limit as delta x approaches 0 of rise over run is what's going to give us our derivative f prime of x. I would ask that you at least, again, have this much written down in your notes. We will very soon after get into this official limit definition of derivative, and I'll leave it up to you if you want to wait until then to write this formula down. But this is the formula that we'll use over and over again in our initial studies of derivative calculus. And I hope you could pause and look at this a little bit and see why that formula is essentially giving us the rise over run and taking the limit as the distance between those 2 points approaches 0. Another thing we spend a lot of time doing in calculus is finding the area under curves. And this is totally separate from derivative calculus, by the way, the task of finding slopes of curves. A separate task is finding the area between, say, this parabola and the x-axis. I won't try to get into why we care about that, how it connects into the real world in this video, but let's just accept that we want to find the area of that parabola, between that parabola and the x-axis. And right now, those 5 rectangles there give us a pretty bad under-approximation of the area we're seeking. What I really want is that grayed-in area there, that shaded area here. So again, right now those rectangles are giving us a pretty bad approximation, under-approximation, but they're a start. And let's now ask the question, what if I were to cram more rectangles underneath that parabola? I'm up to 20 rectangles now, and suddenly it's not quite so horrible an approximation. And if I could find the area of those 20 rectangles, and let me point out, finding the area of a rectangle is very easy. We have a simple base times height formula for that. So if I just apply base times height 20 times on those 20 rectangles, I have a decent approximation of those of the area under the curve. And as I drive the number of rectangles up higher and higher, once I get up to, say, 100 rectangles right now, that approximation is looking actually pretty good. So if I ask the question, how many rectangles ideally would I cram underneath that curve to get the best approximation or to even get the exact area? Well, you're likely to say, I want infinitely many rectangles. I want as many as possible. The problem is infinity is not a number. It's a concept that you're all familiar with to some degree, but we're constrained by the fact that I need an actual number of rectangles, and infinity is not a number. So here's how limits will save the day when we get to that part of calculus. Let's say there are n rectangles crammed underneath that parabola, where n is a real number, an actual positive integer. Of course, the area of any individual rectangle is given by base times height. And I want to add all the individual areas of all those n rectangles, from rectangle number 1 all the way to rectangle number n. We'll use sigma notation, meaning add up all those base times heights all the way from rectangle number 1 up to rectangle number n. Add them all up. And right now, no matter how big n is, all we've got is an approximation. We don't have the exact area under the parabola yet, but if I then take the limit and ask what happens as I take the number of rectangles n and drive it up to infinity. I can't let n equal infinity, but I can ask the question, what happens as n gets larger and larger and larger indefinitely as it approaches infinity? That will give me the exact area under that curve. So I repeat, just adding up a finite number of rectangles areas, no matter how big n gets, that will just give you an approximation. But once you take the limit and let n approach infinity, that's when you can get the exact area of that shaded region underneath the curve there. Of course, the exact details of how we take the limits, we've seen a taste of it in pre-calculus, and this is where we're about to go deeper. But the purpose of this video is to just give you a little bit of sense of where limits are going to be taking us, what kind of tasks we're going to be accomplishing in calculus class using limit. So whether we're finding the slope of a tangent line and using limits to drive the rise in our rise over run calculation closer to 0, or whether we're trying to calculate the area under the curve and trying to drive the number of rectangles crammed underneath that curve up towards infinity, limits will be the tool that we use. Limits will be the key to our success in calculus. Bye for now.